Okay, hello everyone, welcome back. Filming another data analysis video here, and this one again is going to be about probability distributions. Okay, so the last few videos I was talking about the binomial distribution. We're going to move on from that today, and I'm going to, in this video, talk about the Poisson distribution, which is related in some ways. It's quite similar to the binomial distribution. So the Poisson distribution is a discrete probability distribution like the binomial. It gives the probability of an event happening a certain number of times, say k or x, within a given time interval. So slightly different to the binomial. So the Poisson has only one parameter, and that's often referred to as lambda, and this is a rate. So it's the rate at which the event occurs. So it's essentially the mean number of events that occur in a given time period. And an interesting feature of the Poisson distribution is that the mean and variance of the distribution are the same. They are both the value of lambda. So what I'll do in this video is I'll simulate data that follows a Poisson distribution and then investigate that distribution using the probability mass function and the cumulative density function to obtain probabilities of different outcomes. Okay, so let's start off by running this cell and importing some software libraries. So I'm importing pandas as PD, numpy as np, scipy.stats as stats. So scipy is the main one I'm going to use here for the Poisson. I think I'm going to demonstrate how to calculate the PMF for the Poisson using a formula, but I will mostly use scipy because it's much easier. And also matplotlib. .pyplot as PLT because we're going to create a histogram. So the Poisson distribution is useful when we're trying to work out the rate at which events occur. So this could be the frequency with which a certain event occurs in a year or in a week or in a day, that type of thing. So for example, the number of vehicle accidents in a year. So although the Poisson is a discrete probability distribution, as its main parameter is the average number of events in a given year, the mean can take on any real number values and it won't just be an integer value. So the data that's inputted into the Poisson or the data that follows a Poisson distribution will take integer values, but the rate, the mean, can be any real number essentially. So that's still useful, although we can't have fractional occurrences of events in many cases. So for example, we couldn't have half a car accident or a quarter of a car accident. But as is generally the case when you average over discrete integer value counts, you often get a continuous real number average out. Okay. So in the following cells, the following code cells, what I'm going to do is use the scipy Poisson method to generate some data that follows a Poisson distribution, and then I'll use the scipy PMF, probability mass function, and the cumulative density function, the CDF, to kind of investigate and interrogate the data a bit. Okay, so this first cell here, I'm simulating some random data. Using the scipy Poisson method. So the arguments for this method are lambda and the size of the sample we're seeking to generate. Okay, so here what I've done in this cell, I've specified a mean lambda of 1.2. So in terms of positional arguments, I've just put that first, and a data sample size of 100,000 observations. So size equals 100,000 is how many kind of data observations we're asking for. So there are many different examples we could consider to illustrate data that follows a Poisson process in the real world. But what I'll do is I'll stick with the kind of vehicle accident example. So this could be like the average number of accidents each driver has per year. Okay. So note here what I'm doing to generate this data is I'm using the scipy random variance method, so the .rvs method, to simulate the data. I've specified an additional parameter here of random state equals 2. So this is good. This is to allow the results to be replicable by I'm setting basically a seed for the pseudo random number generation process. So here what I'm doing is I'm creating this new object called Poisson underscore RVS, a Poisson random variates. So a variable that follows a Poisson distribution. I'm using the stats.poisson method.rvs.random variates. We're asking for a lambda mean rate of 1.2. Size of the variable is going to be 100,000 observations, and we just kind of set as random seed. So if we run this cell and kind of print out the first 20 values of our 100,000, you can see they're all integer values. Although the mean lambda parameter we specified was a decimal number, it was a floating point number, we asked for a mean of 1.2. So this is obviously a statistical property because you can't have like partial events, partial accidents, say in our case. But if we obtain the mean for this data we've just simulated here, we can see that it will be very close to 1.2, which is the value for the mean for lambda that we specified when generating the data. So if I take our Poisson RVS object and do the dot mean to obtain the mean, we get a mean of 1.19, so very close to 1.2. It's not going to be exactly that because it's random data and there's going to be error and noise in it. So it's in all data sets. So I'm going to do a little bit of manipulation with this so we can plot and visualize this more easily, so we can see what the distribution of the data looks like. What I'm going to do is I'm going to convert it to a pandas series, and I'm basically going to take our random data that we generated, so the stats.Poisson RVS, mean of 1.2, 100,000 observations, and we're going to wrap that in a pd.series. So we're basically changing the original object and we're wrapping it in a pandas series. Okay, I'm also going to create an additional variable object giving the counts of different values in the data. So we're going to create this object called Poisson underscore counts, so Poisson counts, and we're going to take our Poisson RVS object and we're just going to do value counts on it, which will basically give us the frequency of each of the number of events that occurs. So if we run that, what you can see is it's done these in descending order. So we've got one accident, or one event occurred 36,084 times. No accidents occurred 30,000 times. Two accidents to 21,486 times. Okay, so we can see from these value counts that the most frequent occurrence was one accident, 36,084 times in the year. The second highest was 0 accidents, 30,473. And what we can do with these is create a histogram plot showing the proportional probability of each event. And to do this, we want to order the values based on the index rather than the actual counts. So rather than creating a histogram that gives these using Poisson count that would give it in this order, because it's in the order, it's basically in descending order. We want it in the actual event order, so we want 0, 1, 2, 3, 4, 5, 6, 7, 8 rather than 1, 0 as such. So what we want is our x-axis to have in ascending order all of our possible outcomes. Okay, so to reorder the above count data, what I'm going to do is sort the data based on index and then set the Poisson count object to a dictionary showing key value pairings. So we could have done all this in one line above, but I'm kind of just going through each step at a time to make the manipulation of the data more explicit. So I'm taking our Poisson count object, we're doing our Poisson RVS.value counts, and then I'm doing sort index, dot sort index, so sort index method dot to dictionary. So we're making a lot of use of kind of the functionality from pandas here essentially. And if we print out this object, what you can see now is our outcome values accidents 0, 1, 2, 3, 4, 5, etc., and the frequency with which each of those occurred in our data, and they're now saved as a Python dictionary, hence the kind of curly braces gives that away. So we've got a key colon value, so key value pairings is the kind of usual format for a dictionary. So 0, 30,000 times, 1, 36,000 times, etc. So with this kind of object in this format, we can plot the data so we can see the shape of the distribution. And on this occasion, what I'll do is I'll use matplotlib and I'll create a bar plot instead of a histogram. It's kind of analogous to a histogram if we, if we were to normalize our data. But we've got quite a sort of I specifically chose 100,000 examples because it's all nicely divisible by 10 and easy to normalize. So I'm going to create a figure. I'm specifying I want a new figure, and the axis I'm going to create some subplots. Essentially it's going to be 1, and I'm just, if you notice, I'm just passing the Poisson count argument to it. So if I run this cell, what we will see is notice I specified ax.bar, so the type of plot we wanted was a bar plot. And what you can see here is this is the frequency with which stuff occurred on the y-axis and the actual number of events on the x-axis. So that is kind of giving us some indication of the distribution, the shape of our Poisson variable, essentially. We could, like I said, if we normalize this, we could easily convert this to probabilities, essentially, because we got a nice round 100,000 data points. So we can see that this distribution of our data is positively skewed. We've got this tail, this long tail up to larger frequencies and probabilities of events. So events at lower values are more likely, have higher probability, and we've got fewer observations events occurring at these higher values here, very few indeed. So sticking with our car accident example, most of our participants, if we look at this, had like 0, 1 or 2 accidents in a year or in a given time period, and fewer had multiple car accidents. So it's like one person, not many people, I think it was one person maybe had like 6, or one person had 8 accidents, something like that. Obviously very accident prone or very poor driver. So the shape of this distribution here is typical of data that has the characteristics of the Poisson process. Okay, so we can investigate the properties further using the probability mass function. So basically what I'll do first of all, and then I'll use SciPy, is I'll kind of define a function that calculates the probability mass function for the Poisson. And that function is going to take 2 arguments. It's going to take k, which is the number of events, and lam, which is the lambda, the rate, the mean, and return a probability of seeing that number of events given the rate, given lambda. Okay, so this equation, so I'm basically defining a function. So I'm using def reserved word, Poisson underscore PMF is what I'm going to call it, and it's going to take 2 arguments, k and lambda. And what it's going to do is return lambda raised to the kth power times the e to the negative lambda, all divided by the factorial of k. Yeah, our mean, essentially. So this equation here is the function, the equation for the probability mass function of the Poisson distribution, and it can be found in most probability and statistics textbooks. Okay, so let's run that, and then what we can do is we can now call this function we've created and pass arguments to find the probability of a particular value. So for example, if we wanted to know the probability of observing 0 accidents when we've got a lambda rate of 1.2, which is what we simulated in our data, essentially our 100,000 data points, what we will find is that the PMF, it returns a probability of 0.30, so about a 30% chance of a participant having no accidents when we're kind of modeling a process that follows a Poisson distribution and has this kind of mean rate of event occurrence. Okay, so we define the function here to calculate the PMF. This was largely to illustrate that this equation here is specifies the Poisson PMF. I'm kind of looking at that now. Oh no, I thought I'd missed a bracket, but I haven't. However, SciPy already has a PMF method that we can use directly, and this makes it easy to obtain probabilities such as this one we obtained here. So I've created a function here, and we've used that to work out. We've used the PMF formula for the Poisson, and we've used that to obtain this. But we could have just used the SciPy PMF method, which is much easier to use, save us coding our own functions. So let's do that. Let's kind of use the stats.poisson.pmf method, passing the same arguments that we used above. So we 0 accidents when we've got a mean rate of 1.2 accidents per year, and what we find is we've got 0.30. So we're getting the same value as we got above there using our own function. So that's working. That self-defined function is a nice check that that's working properly. But obviously much easier to use this from SciPy stats rather than creating your own functions. So as we created a data set with a kind of nicely rounded sample of 100,000 data points or observations, the probability of observing 0 accidents, about 30%, corresponds closely to the frequency count of zeros in our data set. That was like 30,473. If we scroll back up and look at that, 0.3473 there on that line. Okay, so with using a sample like 100,000, that's very easy to divide by tens. We could have approximated this manually by putting our data on a scale from 0 to 1. And that would, if we did that, that's kind of known as normalization. And to do that with this kind of sample size, 100,000, all we'd have to do is divide through by the sample size. So if we kind of divide the number of 0 counts through by the sample size, so we had 30,473 events or recordings of observations where participants didn't have an accident in a year. Yeah, what we will see if we run this cell is it's still roughly about 0.3. It obviously matches. We've just divided this by 100,000, so it obviously matches that value. It's not going to be exactly the same as our PMF value here, but that's to be expected, as there's always going to be error in our data. And remember, the mean for the data, it was close to 1.2, but it's not exact. Okay, when we simulated this data, it was like 1.19 or something like that. Okay, so that's the PMF, and obviously we were able to kind of normalize this and get a rough idea of the proportion of participants that hadn't had any accidents, because we'd worked with a nice round 100,000 observation data points. We could also calculate the cumulative density function, the CDF of the Poisson, using the SciPy.CDF method. So I'm not going to create a manual self-defined formula here for this, or function for this. You'll probably recall from previous videos that the CDF is a continuous distribution function, and it gives us probabilities between intervals, essentially. So it gives us the probability of observing a certain value or lower in our data set. For example, it gives us, it's kind of sums cumulatively to 1 across the whole distribution. Okay, so the SciPy CDF method takes the same arguments as the PMF. So it takes kind of lambda, it takes a lambda, and the number of events that we want to know the probability of. Or in this case, it's kind of we're not asking for a specific number of events, we're asking for that number of events or fewer when we use the CDF. So here, what I'm going to do is we're going to call the CDF method and see the probability of observing 2 or fewer accidents given a rate per year of 1.2 accidents. Okay, and what we should see here is if we round that to 2 decimal places, we see there's kind of about an 88% chance of P equals 0.879 probability that someone will be in 2 or fewer accidents in a given year, and that kind of matches if we look at our distribution here, like 87, so about 88% of the values are captured by, you can see the distribution, most of the values here are 2 or lower, so that kind of that makes sense and confirms, when we just look at the visualization of our distribution of our data. Okay, so that's the Poisson distribution. It's a discrete probability distribution. It expresses the probability of a given number of events occurring in a fixed interval of time or space if these events occur with a known constant rate, so mean rate lambda. Okay, and we can generate or simulate data that follows a Poisson distribution using the scipy.poisson.random variance method. We can then investigate the properties of our data visually and obtain probabilities of observing specific values using the probability mass function, the PMF. We can also use the cumulative density function, the CDF, to obtain probabilities for intervals in our data, such as the probability of observing k number of events, such as 2 accidents or fewer in a given year. Okay, hope that was helpful, hope that was interesting. I'll move on to a different distribution in the next video, but thanks for listening, and speak to you soon.